So my name is Nick, and my talk is entitled So You Think You Know Swift. This was originally a 45-minute talk, and after much agonizing about what to cut out, I ended up adding another 3 slides, so I'm sorry if I go a bit fast. So, Swift is built on the principle of progressive disclosure. Basically what this means is that it's easy to learn, but hard to master. And a lot of people know some Swift, but almost nobody knows all Swift. And that includes myself, but hopefully today I'm going to show you at least something that you haven't seen before. So I'm going to start with the humble for loop. You often have a situation with for loops where you want to apply some logic only to some of the elements in a list, for example. And you probably do that by nesting an if statement. But there's actually a nice clause, a where clause, that you can add to your for loop, so you avoid that extra level of nesting. But let's say you have a scenario where maybe you have a list of optionals and you want to unwrap the non-nil ones. And you can't use a where clause for that because you can't bind new variables inside a where. What you can do instead is you can use a case let. So this basically lets you bind your non-nil string variable inside your loop and then use it directly inside the loop without any further conditionals. Case let isn't just for unwrapping optionals. You can actually use it for other things like typecasting, or I guess in this case it's more like type filtering. So we have a list of any value, and we're only interested in pulling out the strings. So you can use this sequence of keywords to do that. I'll leave it up to you to decide whether that's preferable to the alternatives. Another cool thing you can do with loops, so you often run into this situation where you've got like nested loops, and you want to break out of the outer loop from inside an inner loop, and you can't easily do that because the break statement binds to whatever its kind of local scope is. But in this situation, you can actually label your loop. You can give it a name, and then you can apply your break to the specific loop that you're interested in. This also works with continue and so on. And this also can be quite useful if, say, you have a loop containing a switch statement, and you want to break out of the loop from within the switch statement. But again, your break is going to bind to the switch by default. And actually, labels aren't limited to loops. So you can also label an if statement, for example, and break out of that. And this is particularly interesting because normally break doesn't bind to if at all. Like you can't break out of an if statement normally. But if you've given it a name, then you can target it for breaking. And this also works with other things like a do condition, for example. So let's talk about strings. So strings are kind of, I mean, everybody knows strings, right? They're sort of the hello world type of most languages. And Swift strings are pretty similar to strings in other languages at first blush. So, if you've used strings in Python or C or Objective-C, like you kind of know what you're going to get. But Swift strings have a reputation for being difficult to work with if you're trying to do anything kind of complicated. So let's say you want to get the nth character of a string. In C, that's very easy. You just give the index and you get the character you asked for. Objective-C is a little bit more verbose because, it wouldn't be Objective-C if it wasn't, but it's still basically the same idea. And then you've got Swift. And what on earth is going on here? So you've got this very long, complicated expression to do what should be a very simple operation. You've got to mention your string variable multiple times. You've got to get an index and offset it and so on. So, why have they made it this difficult to do? Well, the answer, predictably, is Unicode. This slide originally was titled Unicode Ruined Everything, but I was asked to tone it down. So Unicode is great, we love Unicode, but it does cause some problems for some languages, shall we say. So I've got this Unicode string, and appropriately it's a clown car. And in C, I'm trying to pull out the second character. I'm asking for index 1, and it's just giving me garbage back. So I'll try it in Objective-C. Objective-C is kind of Unicode friendly, right? That ought to work. Absolutely not. It's actually only Swift that does this right. Very few languages get this right. I think Rust is another one, but it's a very short list of languages that actually handle this correctly. So why is that? Well, if you look at what's actually going on under the hood with a string, strings have an encoding. So in Swift and C, that encoding is typically UTF-8. C doesn't actually really have encodings. It's just kind of a bag of bytes, but the bag of bytes are normally UTF-8 bytes. And so your clown is not actually one character in this encoding. It's four separate characters, or four separate bytes. And so what happens in C, which doesn't really understand about encodings, is that when you're asking for the second byte, you're just getting the second byte of the clown rather than the next character along. And even in UTF-16, which Objective-C uses, it's using 2 16-bit pieces for your clown. So when you ask for index 1, you're getting the second half of the clown rather than the car. So I mean, fine, Swift has its reasons for making this complicated, but why not just build a nicer API around that? I mean, it's pretty trivial to wrap the horrible API in a nice, simple API and give it the same, ergonomics as C gives you. And so, you can do this yourself. It's kind of a one-liner. But why doesn't Swift just give you that out of the box? Well, the answer is actually performance. So the problem is that in languages like C, you expect to be able to get the nth character as a big O of 1 operation, basically an instantaneous thing. And if Swift offered a similar API, but which actually had very different performance, then you'd have the problem that people would be porting C code to Swift and then saying, why is Swift so slow? It's a terrible language, blah, blah, blah. Rather than having this kind of attractive nuisance of an API that looks like it ought to work nicely, but is actually super slow, it's better just not to give you the option at all and make it clear that because the API is hard to use, maybe you shouldn't be using it that way. OK, so let's talk a bit about optionals. So there's two syntaxes for optionals in Swift. The top one is kind of syntax sugar for the bottom one. But you might be sort of forgiven for thinking these are essentially equivalent. But there is actually one case in which they're different. So when you're using a synthesized constructor for a struct, basically, this nice feature of Swift where you don't have to write the initializer yourself as long as it's internal. If you have an optional property that's using the question mark syntax, then it turns into an optional parameter in your initializer. So basically, you don't have to specify it at all, which is often very convenient. The problem is that this can cause bugs. So if you have a situation where you have an existing struct and you later add a new property, and you're expecting the compiler to tell you all the places that you were supposed to set it, but it doesn't because it's optional. So you accidentally end up not setting it somewhere, and maybe you forget to inject a dependency somewhere that you meant to do it. So to avoid this problem, you can actually use the longer form optional syntax. And this has the subtle distinction that then in your initializer, it becomes a mandatory property. It's still an optional, but you have to explicitly say that it's nil if you want it to be nil. But what actually is an optional? Well, an optional is a monad. And what is a monad? Yes. But it's kind of complicated thing to explain. But better people than me have tried. But I like to think of a monad as basically being a box containing one or more things. Perhaps a more technical description is that it's a type that can be mapped or flat mapped. So yeah, an optional is kind of a collection. You can think of an optional as being sort of a collection of 1 or 0 items. It's like an array that can only have 1 or nothing in it. And in fact, this was actually how optionals were originally implemented in a very early version of Swift before the more sort of sophisticated modern implementation came along. So why is it useful to be able to map something which can only have one element in it? Well, you can actually use map for unwrapping optionals. So often when you have a situation where you want to do something only if the optional is non-nil, and you want to do something to the non-nil value, you'd use the if-let syntax. But you can use map in this case to sort of apply a function that is only executed on the values inside, which in this case is either something or nothing. It's kind of sometimes a little bit controversial to do something like this, where it's not technically returning a value, so maybe it's like a violation of functional principles, but I like it. OK, but what is an optional really? I mean, you could be forgiven for thinking that an optional was maybe a pointer, something like that. And in Objective-C, that's basically what it is. It's just some like sort of attribute that you apply to a pointer to say that this can be nil. But that wouldn't make sense in Swift, where even something as primitive like an integer can be an optional. In Swift, an optional is actually an enum. And it's a generic enum. So it's an enum which can either be nothing or t, where t is the type that you provide. So let's talk about enums. So, I mean, we've all seen C-style enums, which they're basically just syntax sugar for a collection of integer constants. Swift extends that with string enums, which can be super useful as well. And Swift enums really come into their own when we're talking about enums that have associated values. These are sometimes called tagged unions in other languages. So the enums where each case can wrap a value maybe of a different type in each situation. When you're comparing enums, when you're checking whether a particular value of an enum is a particular value, they're equatable by default, which is quite handy. So you can just use equals. But when you've got an enum with associated values, this doesn't really work, because in the case of, say, like an HTTP response, where you want to check whether the response was OK, you don't want to have to pass the body that you were expecting to see if that's what you got. You just want to check if it's OK and then get it to give you the body. So in order to do that, you need to use pattern matching. So let's talk about pattern matching. So we mentioned the if case let syntax earlier, or the case let syntax earlier. And I mean, this works. It's hard to love as a syntax. This is sort of like so well known. There's actually a website dedicated to this fact, and the website comes in two flavors: work safe and not so work safe. It borrows from the grand tradition of the effing block syntax from the Objective-C days, which was another particularly unlovable API. So instead of case let, you're probably going to want to use switch, which is the kind of the maybe more familiar way of doing this. And there's actually there's some other good reasons for using switch rather than if case let, which I'll get to in a second. But case let, these syntaxes are all effectively equivalent. So you can use switch, you can use if case let, you can use guard case let. They all do the same thing. Where case let is quite useful is that you can use it in context outside of if. So the for case let I mentioned earlier is quite handy. You can also use while case let. And there's actually a version of this for do catch statements. So it doesn't use case, it just uses catch let, but it's basically the same thing. It lets you do pattern matching on errors that are thrown inside do catch. So let's talk about switch case. So switch case isn't only limited to matching optionals or unwrapping enums. It can also be used for other kinds of pattern matching. So for example, you can match whether an integer value is inside a particular range, or for that matter, a floating point value. You can also match if you can match the type of the thing that you're passing in. So you can say, is it this type? Or you can unwrap it as that type. And in fact, you can add a where clause to your cases as well. So that if you want to check both your pattern matching and also maybe some other condition as well, you can do that. And if you use a wildcard for your case matching, you can effectively build a sort of fancy if-else statement this way by just ignoring the value that's passed in and then just applying some logic in your where clauses. It's also possible to create your own patterns. So there's the tilde equals operator basically lets you define, instead of a equality comparison, it's a kind of pattern matches comparison. And if you define this for your own types, it lets you use them in switch cases to match. Let's say if you have some kind of custom sort of collection-y type, you can match whether a value is logically inside that type for whatever that means for your particular logic. Something to bear in mind with switch case statements is I've often seen this pattern where you match a particular case, and then, like in this case, we only have two cases. So you're like, well, I'll match if it's portrait, and if it's not, then I'll just assume that it's landscape, because what else could it be, right? And it's very common to just use a sort of a lazy default like this. The problem is that if somebody then comes along later and adds maybe another case to your enum, your logic breaks, but the compiler won't warn you. It has no way of knowing that actually your default is no longer correct in this situation. And for this reason, it's better to use exhaustive switching. So this is a really nice feature of Swift, where basically if you explicitly handle all cases and don't have a default, then if somebody comes along and adds another case, the compiler is going to warn you that that case hasn't been handled. Another situation where it's really handy to use switch is if you have a situation with maybe some complicated Boolean logic where you're checking multiple different Boolean variables, or indeed any kind of variable really. It's very easy to sort of accidentally miss branches in your logic. There's a case here where we checked if you're logged in and if you're an admin, but we forgot to check for the case where you're logged in and you're not an admin, and then maybe we've introduced a bug because of this. And the compiler, again, isn't really empowered to warn us that we've missed that case. But if you replace this with a switch over a tuple of Boolean values, then it lets you create an exhaustive switch over essentially what's a truth table. So you can basically make sure that you handle every possible scenario in this case. And if there are cases you don't care about, you're still free to ignore them using an underscore as a wildcard. So rather than using a default here where if I'd forgotten a case, it wouldn't be able to warn me, by explicitly just saying, well, I don't care, if you're not logged in, I don't care if you're an admin, I can just target that specific case that I want to ignore, but it will still warn me if I've forgotten about anything else. Okay, so in Swift, there are value types and there are reference types. Value types are typically they're stored inline, maybe on the stack. They're copied every time that they're used, and they tend to have a fixed size. Reference types, on the other hand, they'll normally live on the heap. They're shared between call sites, so if you make copies of them, they're basically all references to the same value. And they're dynamically allocated, so they can change size at runtime, for example. So as we all know in Swift, classes are reference types, whereas structs, enums, and tuples are all value types, right? It's not exactly the case. So I'll give you an example. I've created here a struct. It's a node. Maybe it's a node in a linked list, for example. And I want to use a struct for this, but I can't, unfortunately, because it's not really logically meaningful for a struct to be able to contain a copy of itself. It would basically have to be infinitely large in order to be able to do that. And even if, in this case, my parent node is optional, that doesn't really help, because as we saw before, optionals are enums, and enums are also value types. So it would still require infinite storage in order to work this way. And yet, if I was to make this something like a tree node, which has multiple children and contains an array of other nodes, this is absolutely fine. The Swift compiler is quite happy to let me do this. And the thing is, arrays are structs. They're value types in Swift. So how is this possible? Well, the answer is that if you look at the implementation of how array works, yes, it is a struct on the surface, but that's really just a facade. What's actually happening internally is that it's a class. So it's a value type, but it's got a lot of the semantics of a reference type in terms of dynamic allocation, ability to grow at runtime, and so on, and it's actually stored on the heap. So if it's following, if it's got a reference-based implementation, how is it still managing to maintain value semantics? Well, the answer is that it uses a paradigm called copy on write, or COW for short. So copy on write is a mechanism that Swift uses to basically allow classes to behave like value types, where when they're copied, changing one of them doesn't change all of the other ones. And the way this works is using a function called isKnownUniquelyReferenced. So basically, whenever you try and mutate an array, the subscript implementation of the array checks whether its internal storage is being used by any other copies of that array. And if there are any other references to it, it will make a copy of the entire array, mutate that, and then store that copy internally so that in future it's going to be mutating that one instead. Hence, copy on write. When you're copying it normally, it doesn't need to do that, and so you have a lower overhead. Now, there's quite a lot of myths about copy on write in Swift. I think there's a perception maybe that this is kind of one of those magic things the compiler just takes care of for you. The reality is that Swift never implements copy on write for you. It's not something where it's just like, oh, my struct's kind of big, like maybe the compiler will sort of turn it into a class under the hood. You have to do all of that work yourself, and it is quite a lot of overhead. It's overhead both in terms of implementation, like difficulty and complexity, but also actually in terms of performance as well. Because of all the automatic reference counting and heap promotion and everything that has to happen, it's a lot more expensive to have a struct that's backed by a class than just a regular struct. It can, however, still be the lesser evil in terms of performance in some cases. Something that happens when you have a struct containing multiple copy on write types, so for example, if you have a struct with multiple arrays inside it, is that every time you make a copy of that struct, it's got to increase the retain count of all of the internal storages of all of the properties inside it. And that can actually have a significant impact if you're doing something like this in like a hot loop in your code. And so you might actually find that with a case like this, it's more efficient if you wrap all of those properties inside a class and manage the copy on write logic yourself. So enums, like structs, also cannot contain themselves by default for exactly the same reason. They'd have to be infinitely large. But with enums, there's a really nice solution to this, which is the indirect keyword. So the indirect keyword lets you mark either the whole enum or just a particular case as being stored like out of line of the enum itself, which allows for it to have self-references. There has been talk about adding an indirect keyword that works with structs as well, but it's not currently gone anywhere. But yeah, this is a much nicer way of implementing the kind of copy on write pattern, for example, without having to do all of that logic yourself. So we know that structs and enums are values and classes are references, but what are protocols? Are they values or are they references? Well, the answer is it depends. So a regular protocol is actually a value type. It can represent a value type or it can represent a class. But there are also class-bound protocols, so protocols that conform to any object, and those are reference types. So let's talk a little bit about class-bound protocols. So they get some like extra capabilities versus an ordinary protocol. You can use the weak reference keyword with them because it knows that it's a reference, so it can be a weak reference. And you can also use the triple equals identity operator to basically ask if two instances are the same, which isn't possible with a normal protocol. They also have a lower overhead. Basically, they require less storage. I'm going to talk about that in a minute. But if you can use a class-bound protocol, you're generally better off doing so. Basically, if you know that everything that's going to implement it is going to be a class. And they actually have this nice feature that they can be restricted to a specific base class. So rather than any object, you can say, well, this protocol only makes sense in the context of, say, a view. I did try and find a more server-side relevant example of this, but I had to look at Vapor, and all of its classes are final, so that doesn't really make sense. But imagine that this is a class that you care about. OK, so here's an example of a class-bound protocol. So I've got my protocol foo, any object, and I've got my concrete classes bar and baz, which both implement my foo protocol. And I've got this variable foo, which is, sorry, I used foo too much, but insert your own name here. Foo is of type any foo. And the question is, like, what actually is that? Like, how is that represented? And the answer is that it's just a pointer. Right? It's a pointer to some class, so that's fine. And I can assign bar to it, and then I can change it to baz, and that's OK, because pointers are pointers. It's interchangeable. I can swap them around at runtime. And that requires 8 bytes of storage. It's actually sometimes 16 because of witness tables, but we don't need to go into that. But then let's talk about what happens with the regular protocol. So this isn't a class-bound protocol. It could be anything. I've got a struct bar that implements it. I've got a class baz that implements it. Basically, anything that conforms to foo can go here. And so if I've got a variable of type any foo, like, what is that? How does that work? How can I allocate storage for something that could be literally any size? How big actually is that variable in memory? Well, to answer that, you have to understand how something called existentials work. So what is an existential? Existentials get their name from the axiom that there exists a type T. There exists, you see, a type T such that T conforms to the protocol. You can read about them in the Swift book. So what is an existential? Well, it's basically the actual type that exists when you're not sure what type you have. And existentials are represented using an existential container. This is the C++ code that is the implementation of an existential container in the Swift runtime. This is a struct, and it's 40 bytes in size. So the answer to the question, how big is something when you don't know how big it is it's 40 bytes. So this struct has a few things inside it. It's got some metadata. We mentioned witness tables before. The interesting part here, though, is this fixed-sized buffer. So there's a buffer inside the existential container. It's 24 bytes. And this is where your actual value gets put. So let's say you've got a struct that conforms to your protocol. If it's 24 bytes or under, it just gets put in line inside there, and it's all good. You're done. If it's more than 24 bytes, it has to be stored somewhere on the heap, and a pointer to it gets put inside this buffer instead. And so you have this interesting performance cliff, where if you're using protocols with structs, if your struct suddenly goes from being 24 bytes to 25 bytes, it can have a sudden performance impact where a bunch of stuff that was previously living on the stack and like having nice cache locality is all suddenly spread all over the heap, and your performance falls through the floor, and you're not really sure why. And this is one of those like interesting little performance details where, unless you actually understand what's going on under the hood, there's no possible way that you could expect or predict that would happen. So I mentioned before any foo, but there's also this syntax some foo, and some and any are relatively new keywords to the Swift language. What is the difference between some and any? Well, any is basically, it means that this is a value where it can change at runtime. It could be anything that conforms to this protocol. Some is a little bit different because although you don't know what type it's going to be, you know that the compiler will know what type it is when it's actually building your app. So any is for when you don't know at runtime what type it's going to be, and some is for when you don't know at compile time what type it's going to be. And because of this, some is potentially quite a lot more efficient to use than any. There's only going to be like one specific type. It's not going to change. And so the compiler can maybe optimize it. Maybe if there's only one type in your whole application that conforms to this protocol, it can just be inlined, and it doesn't need to do any of this messing with existential containers at all. So we talked about value versus reference types, but another way of dividing types in Swift is nominal versus structural. Nominal types are ones which are unique because of their name. Structural types are ones that are unique because of their structure. Classes, structs, and enums are all examples of nominal types. So if they have different names, then they're different types. Tuples and closures are examples of structural types, where it doesn't matter what they're called. As long as they have the same structure, then they're interchangeable. I'll give you an example. So for nominal types, I might have a user ID and a service ID. These have the same structure. They're both basically just string wrappers. But because they have different names, they can't be used interchangeably. Here I've got an example. I've created Bob, which is a user, and prod, which is a service. And I'm not allowed to compare them because they're not the same thing. They're apples and oranges. And yet, if I was to use tuples to implement these, and I've created type aliases here just for sort of readability, but it doesn't actually make any difference to the type. My person is obviously, it's a person, it has a name and an age. My address has a street and a house number. But as far as Swift's concerned, these are both just tuples of string and int. And so even though I can look at this code and see that logically it makes no sense at all to compare these things for equality, as far as Swift's concerned, it's perfectly okay, and they can be exactly the same thing. I mentioned that closures are another example of a structural type. Let's talk about closures for a bit. So you've all seen closures before. They're kind of sort of backwards functions where the parameters go after the curly brace. This is the typical syntax you might use to declare a closure. What you may not realize is that all of these things are also closures. Regular functions are closures, methods are closures, initializers are closures, and even enum cases are also closures. They're all closures. And because closures are structural types, different types of closure can be used interchangeably as long as their signatures match. In this case, I've got a function, print type interface, that takes a callback, which is a closure, and it accepts a Boolean parameter and it returns a typeface. And I have an enum typeface, which has a case, which has a Boolean payload. And in actual fact, that can conform to this protocol, to this closure signature. So I can pass my case directly to something which is expecting a closure, and because the signatures match, it's perfectly happy to accept it, and the code will work fine. It's not immediately obvious why this would be useful, but a slightly more useful case is when you're dealing with something like a method instead. So here's an example with a method where I've got a for each, and I'm passing it a closure to add a subview. Again, sorry about the views thing. I'm basically an iOS developer at heart. But you can simplify this. You can just pass the add subview function directly, which is, it saves you some typing, which is always good, right? There is a danger to doing this. So you're all aware of the problem with retain cycles in Swift. And in a situation like this, where you've got an update handler function, and you're using a closure, the compiler is going to warn you here that, oops, you're accidentally capturing self. And in order to suppress this warning, you would need to explicitly mention self in the capture list. Maybe you'd mark it as weak self to avoid the retain cycle here. But if you try to be clever and just call the default uphandler method directly from passing it as your closure, Swift isn't going to warn you anymore. This works perfectly well. It's just you've created a retain cycle here, and the compiler isn't going to let you know that you've done it. So generally speaking, it's probably maybe not a good idea to do this. Where it is a much better idea to use this paradigm is for initializers, where you don't have this risk of a retain cycle, because you can't create a retain cycle if you're passing an initializer, because the object doesn't exist yet. So this is quite nice from a sort of syntax sugar point of view, but it does actually have a pretty handy real-world use case. I'm going to talk about that in a second, but first, a little discussion about factories. So factories are a solution to a problem that we all encounter when it comes to testing. So you've got a class like tool user, and internally it's creating a hammer, and it's doing some stuff with that, and that's all great. And then you get to the point where you want to test it, and you realize this is really very untestable code, because you don't know what dependencies it's using internally. You can't get at them. You can't mock them. You can't see what's happening inside these classes. You don't even know it's using these classes. And so the standard solution to solve this is that we use the factory pattern. So you have a hammer factory, or rather you have a hammer factory protocol. The hammer factory creates the hammer. You can replace your hammer factory with a mock hammer factory and so on. And this does involve quite a lot of boilerplate code, but it's the only solution. Like, this is well established. This is what we have to do, right? I'm not a huge fan of this pattern, I would say. It has a bit of a sort of Java design patterns from the 90s enterprisey feel to it. I feel like we can do better than this. Swift is a modern language. It has closures. And all of this boilerplate can just go away and just be replaced with a closure. I mean, in a sense, what is a function if not a factory? It's a thing for making something and returning it to you. So we don't need a protocol. We don't need concrete implementations. We can just have a closure. The usage for this is pretty much the same as it would be for the protocol-based version. We have a function which accepts a factory function. We pass in our factory function, and it creates the hammer internally. But this is where the fact that initializers are just closures is quite nice, because here, instead of having to create a closure and a factory function and everything that actually creates our object, we can just pass the hammer's initializer as the factory function, because that's all an initializer is. It's a function that produces the object, so we can just pass it in directly. And if we want to mock it, we just pass the mock hammer's initializer instead. So I did have one more thing. That's a huge lie. I have many, many more things. I didn't actually have time to cover everything I wanted to. I crowdsourced a bunch of cool things from Mastodon, and I've cut down that list to just the ones that I thought were most interesting for time reasons, but I'm going to try and rush through this as quickly as I can. So here's some things I like. We talked about enums before. Swift doesn't have namespaces, which is kind of annoying, but empty enums actually make great namespaces, because the thing about an empty enum is you can't instantiate it. There's no real object there at all. You can't make an empty enum. It just exists as a type into which you can put other things, and so it's great for using if you want a namespace. By default, everything in Swift, as you probably know, is module scope. But sometimes you have a bunch of things that you want to make public. And instead of having to mark all of them public, you can just put them in a public extension, and then they all become public by magic. And it's super handy because maybe you can mark them as private initially, and then if you want to change them to public later, you just have to change one line instead of hundreds. There's a nice new thing in Swift 10.10. Protocols can now finally be nested inside other types, which is a great relief. It's the one thing that you couldn't do. It was so annoying. Another really annoying thing is if you have a string and you want to convert it to data because you need data, but it's an optional. Why does it return optional? It can never fail. So annoying, but there's this alternative syntax you can use, which is, I only discovered this recently, but it's changed my life. If you have long numeric literals, I don't know if you knew this, but you can use underscores to break them up, which is a really nice feature. And this last one, I included mostly as a cautionary tale. So when you're writing unit tests to test your JSON outputs, you've probably run into the situation where you paste in your JSON and then the unit test fails because the order of the JSON and when it's generated isn't deterministic. So you can mark, on your JSON encoder, you can mark the output formatting sorted keys property, which will mean that it always generates the keys in a persistent order, which solved this problem. And it solved this problem for many years. And then Apple broke it in iOS 18. So they changed the order. So I guess it's going to be consistent from now on again, probably, hopefully. But yeah, maybe don't rely on that after all. Anyway, that was all I had for today. Thank you.